Welcome to this lecture number 26 on this NPTEL course on fluid mechanics for undergraduate chemical engineering students. The topic we are discussing in the last lecture was differential momentum balances, and we applied it to two case studies. One is that of plane cuvette flow, which was driven by the relative motion between two rigid plates. So, the bottom plate was stationary and the top plate was moving with a velocity u, and then we found out that after solving the problem that the velocity profile is linear in the y direction. Suppose you put a coordinate system, the flow direction is x, normal direction is y, and the plane out of the board is z, and we found out that the velocity profile is linear in the variable y. So, if you want to write the velocity profile V x, so we write the velocity vector as u v w. This is the component in the x direction, this is the component in the y direction, this is the component in the z direction. The steady velocity profile, okay, that emerges in this gap is given by u of y is capital U times y divided by h. Okay. Using this, you can find what is the shear stress exerted by the fluid on the solid surface, that is simply mu du by dy. This is the force that is exerted by the fluid on the solid surface. So, this is mu times u divided by h. We also found out that this force has a sign convention. So, this is the direction of the unit normal of the surface on which the force is acting. Okay. And this is the x is the direction of the force itself, is the direction of the force. Now, in this application, the unit normal is pointing in the minus j direction, that is in the minus y direction. So, as per our sign convention, if you find that all these quantities are positive, mu is positive, u is a scalar number, it is a magnitude of the velocity of the top plate, and h is positive. So, this is greater than 0. This means that a force of mu u by h acts on a surface whose unit normal is in the minus j direction, and the direction of the force is in the minus x direction or minus I direction. Okay. The force, the drag force exerted by the fluid on the top plate is in the minus I direction. If you look at the bottom plate, okay, so we will just go a little bit down, and then if you look at the bottom plate, the unit normal is in the plus j direction. Okay. Therefore, the force exerted by the fluid on the bottom plate, the drag force will be in the plus I direction. Okay. So, using this shear stress, you can find what is the force exerted by the fluid on the top plate, that is equal to mu u divided by h times the area. Okay. Now, the rate at which work you must, so essentially you have to apply an force, this force acts in the direction in minus I direction. This is the magnitude of the force, the direction of the force is minus I. Okay. Now, if you want to move the plate at a particular velocity, okay, so the force to be exerted on the plate is mu u divided by h times a, and this force should act in the plus I direction. The force, an external agency that should which should exert on the plate so that the plate moves at a constant velocity, is plus mu u divided by h a, and an equal and opposite force is exerted by the fluid below the plate on the plate in the minus direction, minus I direction or the minus x direction. The sum of forces cancel out, so that the plate moves with a constant velocity u. Okay. So, this is the idea. We also found out that we can calculate what is the rate at which work must be done on the top plate. That was simply rate of work is simply the force times the velocity. So, it is mu u h divided by a times u, so mu u squared h divided by a. This is the rate at which work must be done on the top plate in order so that the plate continuously moves at a velocity u. Okay. So, now the next problem we turn to is the plane Poisson flow. Okay. Now, this flow is the flow between the space gap between two long and wide plates. Okay. You imagine you have a slit like distance between two long plates. So, let the length of the plate be L and the width of the plate be W, and we are going to assume that the flow is in the gap between these two long and wide plates. The flow comes in like this and goes out like this. Okay. So, it is convenient to put a coordinate system to begin with. The direction of the flow is x, the direction normal to the flow is y, and the direction out in the width direction along the width of the plate is z. Okay. Now, we are going to further assume, we said in the last lecture, that L is very large compared to h. Okay, let us call the width of the plate as 2b. Okay, the gap between the two plates through which fluid is flowing is twice b. So, b is essentially the half width. So, L is large compared to b, and we also said that the plates are very wide, W is large compared to b. Okay. And the reason why fluid is flowing in the plus x direction is that there is a pressure difference between these two, between the entry and exit. So, there is a delta p, there is a pressure difference. So, p at x equal to 0 minus p at x equals L is what we call as delta p, the pressure difference between the beginning of the gap and the end of the gap. Okay, and that pressure difference drives the flow. We made several assumptions in order to proceed further. Those assumptions were steady, flow is steady. That is reasonable, because if the applied pressure difference is invariant with time, you would expect that the velocity that flows in between the two plates should also be steady, that is independent of time. Flow is fully developed. That is, there is no variation of the fluid velocity profile in the direction of the flow. If you go along the flow direction, u, the velocity profile, okay, in velocity independent of flow direction. This is the fully developed assumption. The third assumption is the flow is two dimensional, okay, in the sense that there is no variation of the velocity u in the third direction along the width of the plate. So, there is no variation along the z direction. Okay. The flow is strictly two dimensional. This means that no variation along z direction, because the z direction, the width of the plate is so the flow direction is x, the width of the direction along the width is z, and the direction along the gap is y. After making these assumptions, okay, and we found that the continuity equation or the mass conservation equation, partial u partial x plus partial v partial y plus partial w partial z is 0, because the third direction is so large compared to the other two directions and there is no driving force for the fluid to move in the z direction, we can say that the this term vanishes. There is no w velocity, there is no velocity in the z direction. We also said that there is flow is fully developed. So, fully developed flow means that du dx is 0, 2D flow means that dw dz is 0. Then the mass conservation equation simply implies dV dy is 0. Now, if you look at the flow geometry, okay, at y equals minus b and plus b, okay, b, the velocity v has to be 0 because these are rigid walls. So, the fluid cannot penetrate into the rigid walls, they are impermeable rigid walls. So, v, if you partially integrate this, v should be a constant with respect to x, okay, because dv partial v partial y is 0, but that constant should also be 0 because at y equals plus b, v is 0 at all x plus or minus b, okay, at either of the two plates plus b or y equals minus b, the velocity is 0, the vertical velocity is 0. So, it has to be 0 right across the entire channel. So, there is only one velocity u in the flow direction and it can be a function only of the normal coordinate y. So, this is the information we have so far obtained from the continuity equation. Now, we will go to the x momentum equation. The y momentum equation will simply tell you that partial p partial y plus rho g y is 0. If you align the gravity vector, okay, in this fashion, let us say this is x, this is y. If gravity is acting in this minus y direction, okay, then g y is minus g. Okay. So, 0 is dp minus dp dy, I am sorry, minus rho g. This implies that dp dy is minus rho g or p is minus rho g y plus some constant p naught, okay, and that p naught can engender some constant c, could be a function of x because we are only partially integrating with respect to y. So, this is the information we get from the y momentum balance. What we can conclude from here is that if I take the partial derivative of this with respect to x, the first term vanishes because we need this in the x momentum equation. So, we will simply get partial c of x by partial x, it is only a function of x, it is only a function of x, okay. It cannot be a function of y from the y momentum equation. So, the x momentum equation simplifies to, okay. So, let me quickly write down the entire momentum equation. Okay, plus rho g x plus mu the Laplacian of the x component of the velocity. Now, we are going to knock off terms. Steady flow means this is 0, fully developed means this is 0, no normal velocity means this is 0, 2 dimensional flow means w is 0 and rho g x is 0 because the channel is aligned horizontally. So, there is no component of the gravity in the direction of the channel, and this term is 0 because flow is fully developed, this term is 0 because the flow velocity is independent of the z direction. So, after having done that, you land up with an equation 0 is minus partial p partial x plus mu. Okay. Now, this is a function only of x, this is a function only of y, because from the y momentum balance we found that the pressure can be a function only of x, dp dx can be a function only of x, and from the continuity equation we concluded that u is a function only of y. So, each must be equal to a constant. What should that constant be? Okay. So, minus dp dx, okay, minus dp dx is a constant. That means, p is a linear function of x. If dp dx is a constant, okay, then p varies linearly with x. Okay. So, in order for the fluid to flow in the plus x direction, the pressure at 0 must be larger than the pressure at L. Okay. So, minus dp dx is nothing but minus of p at L minus p at 0 divided by L, because the pressure is a linear function of x. So, I can simply take and the partial derivative of any quantity is defined as p at x plus delta x minus p at x divided by delta x. But since it is a linear variation, I can take it to be p at L minus p at 0, but I have defined p 0 delta p as I have already defined the pressure difference as p 0 minus p L, because p 0 is greater than p L. Okay. Okay. Therefore, I can write this equation as minus partial p partial x is minus of minus delta p by L, or it is simply delta p by L. That is simply put, in order for the flow to be in the plus x direction, okay, this is the plus x direction, the pressure must decrease in the plus x direction. So, dp dx is a negative quantity. So, minus of dp dx will become a positive quantity. So, the x momentum equation simply becomes delta p by L plus mu partial squared u by partial y squared, or if I take it to the other side, I can, without loss of generality, I can convert the partial derivatives to ordinary derivatives. I can write the partial derivatives as ordinary derivatives, because u is only a function of y. So, I get delta p by mu L. Okay. If I integrate this twice with respect to y, if I integrate it once with respect to y, I will get delta p by mu L times y plus c 1. If I integrate it twice, u of y will become delta p y squared by 2 divided by mu L plus c 1 y plus c 2. Now, the constants of integration must be found from boundary conditions. The boundary conditions that we know are at y equals minus b, you have no slip, u 0, and y equals plus b, you have u 0. But we could also, as I pointed out in the last lecture, use the symmetry plane at y equals 0 and say that du dy is 0 at the symmetry plane. Okay. Because the velocity profile is completely symmetric, the geometry is symmetric, the boundary conditions are symmetric, the driving force is the same. So, the velocity profile must be a mirror image upside and downside of y equal to 0 plane. So, at y equal to 0 itself, u has to be a maximum, okay, because the flow is in the plus x direction. So, du dy is 0. We will use that, because that is simpler to set this constant at y equals 0, du dy is 0 implies, if I use this equation here, if I put y equal to 0, I get c 1 is du dy, but at y equal to 0 du dy is 0. So, c 1 is 0. Okay. So, c 1, the constant c 1 is 0 in the velocity profile. So, we get, so we can knock this term off. So, at the other constant is found by using the other boundary condition at y equals plus b, u is 0. This implies that 0 is delta p by mu L y squared by 2 plus c 2. So, if I bring c 2 to the other side, I will get minus delta p by L, okay, and instead of y I should put plus b. Okay. So, b squared by 2. Okay. So, the velocity profile u of y becomes delta p by 2 mu L b squared times 1 minus y squared by b squared. This is the velocity profile for steady fully developed flow in a rectangular channel, where the width of the channel and length of the channel is very large compared to the gap between the two plates, that is half, that is b is the half width of the half gap of the channel, 2b is the full gap width of the channel. Now, having derived this, what else can we do with this expression? Well, first thing we can do is we can plot this expression, okay, and this is the center line. Okay. If you want to plot this expression, you will find that the velocity is 0 at the walls and maximum at the center, and it is a parabolic function of the normal coordinate y. the x velocity, okay, is maximum at the center and 0 at the two walls. Okay. So, that is what this solution will say, but we can also get more information from this solution. Suppose you want to ask the question, what is the average, what is the volumetric flow rate that one gets for a given pressure drop inside this rectangular channel. Okay. So, what in order to find the volumetric flow rate, is the volume amount of volume that flows in the channel per unit time. Okay. So, it is denoted by the symbol Q normally. Okay. Okay. Q is defined as integral U times dA, okay, where A is the cross sectional. It is important to note here the area, the cross sectional area through which fluid is flowing. This is W, the width of the channel, and this is 2B, and you are integrating over the, this is the flow area through which fluid is flowing. Okay. So, what is it in this geometry? Q is integral dy y equals minus b to plus b u of y, and then the other direction there is no variation, we can simply type this as w. Okay. So, essentially we are taking a strip of thickness w dy, and since the velocity is a function of y, we have to do the integration to find the volumetric flow rate. And let us substitute what the form of the velocity is in this. We just found what the form of the velocity is here, delta p by b squared by 2 mu L. Let us substitute that here, delta p by 2 mu L b squared, okay, w is a constant, I can pull it out now. So, let me write this minus b plus b dy 1 minus y squared divided by b squared. Now, the integrand is an even function of y, okay. So, whether you go to y equals in the positive direction or negative direction, you will get the same value for the velocity. It's the velocity profile is symmetric about y equals 0. So, instead of evaluating the integral from y equals minus b to b, I can write this simply as y equals 0 to b twice, because I am trying to integrate only the half domain. So, I will write twice dy 1 minus y squared by b squared. So, this is just to use the symmetry of the problem. So, q is, so the 2 will cancel with this 2, q is delta p b squared w, this is b squared by mu L times, if I integrate y, you will get dy, I will just get y, integrate y squared, I will get y cube by 3, y equals 0 to y equals plus b. So, this is equal to delta p b squared w by mu L times, if I evaluate this at y equals plus b, I will get b minus b cube by 3 b squared. If I evaluate this at 0, I will get 0. So, I do not need to do this. So, this is nothing but delta p b squared w by mu L times b minus b by 3. This is nothing but q is delta p b cube w 2 by 3 divided by mu L. So, this is a very important result, because it tells you how the flow rate in a rectangular channel depends on the various parameters such as the pressure drop, the viscosity, the width of the gap thickness of the channel, that is 2b, and the other parameters like width and length of the channel. Okay. So, as for everything remaining constant, if you, so we can invert this relation to write this as, suppose I want to know what is the pressure drop I must maintain in order to achieve a given flow rate. So, I can invert this as 3 by 2 q mu L by b cube w. Okay. So, what this means is that for if I want to fix q, okay, and if I fix the viscosity of the fluid, okay, and length and width, then delta p goes as 1 over B q. That is, as the channel becomes, the gap becomes smaller and smaller, the pressure drop that is required to pump a fluid, okay, in a channel of thickness, that is gap thickness 2b, it goes as 1 over, it is inversely proportional to the cube of b. So, it rapidly decreases as you decrease the channel dimension. Okay. It is a very useful result, especially in the context of newer applications such as microfluidics, where the channel widths are of the order of let us say hundreds of microns, okay, in contrast to conventional applications where the channel widths are fairly large. Okay. So, you get a very quick feel for how large pressure gradients that we must apply if you want to push fluids by pressure drops, okay, inside channels of very small thicknesses. Okay. This is a very useful result that one obtains. One can also obtain from this relation what is the average velocity. Okay. The average velocity V bar is q divided by the area through which fluid is flowing, 2 B W cross section area. So, V bar is nothing but, okay, delta P B squared by 1/3 mu L. Okay. So, this is another important result. It tells you what is the average velocity of the fluid. Okay. We know that the velocity profile is parabolic, which we pointed out repeatedly several times. Okay. The velocity profile is parabolic. Okay. The maximum velocity is in the channel, happens at the center. So, I have to simply put y equal to 0. So, delta p b squared by 2 mu L. The average velocity which we just found out is delta p b squared by 3 mu L. Okay. So, the average velocity is 2/3 the maximum velocity in a rectangular channel through which fluid is flowing. The average velocity is, this is another important result, which we already sort of hinted at when we did momentum correction factor as well as kinetic energy correction factor. We pointed out to the fact that the velocity variations within a channel or a pipe for that matter is not, the velocity flow profile is not uniform, it varies across a cross section, and in that context we had to evaluate the average velocity, and we found that we use these relations without proving. Now, we have actually proved this relation, that the average velocity for flow in a rectangular channel is 2/3 the maximum velocity. The maximum velocity happens at the center of the channel by symmetry, and the average velocity is 2/3 the maximum velocity. Okay. So, this is a very important result again, which we already used in the context of kinetic energy correction factors and momentum correction factors when we did integral balances, but at that time it was merely a statement without proof. Now, we have actually proved it. Okay. So, this is another important result that we just derived. Okay. So, a few comments that I want to make regarding the logic of the solution for Navier-Stokes equations. Okay. Okay. Solution logic. Okay. First, we made some assumptions about the nature of the velocity field. Okay, we said that the velocity field is only, the velocity is only in the x direction. There is no component of the velocity in the z direction, because there is no driving force in the z direction on the first place, and there is no variation of the x velocity in the z direction, because the width of the channel is very large compared to the gap thickness b. Okay, so, we said that the flow velocity small u is independent of z. It could be a function of y, because of course, the no slip condition is valid at the two walls. Okay. So, this is one assumption we made. Then other assumption we made was that of steady flow, which is reasonable, because when the applied pressure gradients are steady, it is not unreasonable to expect that the flow should also be steady. The third assumption we made is that of fully developed flow, that is the flow velocity is independent of the flow direction. Okay. and that is true when you are far away from the entrance and exits, because when you are far away from the entrance and exits, okay, there is no reason for the flow velocity to vary in the flow direction. Okay. With these assumptions, we proceeded to solve the momentum equations, and we threw away several terms, okay, and ultimately we landed up with a solution for the velocity profile in the x direction, and it depended only on the y coordinate. In terms of geometrical coordinates, of course, it depended on viscosity and the thickness of the channel and so on, the gap thickness and so on, but in terms of coordinate variation, it is a function only of y. Okay. Once you did that, we got a consistent solution, in the sense that the solution that we arrived at does not contradict any of the assumptions we made. Okay. In more complex flow situations, it could happen that you could make an assumption and the continuity equation will say that that assumption cannot be made. Okay. So, it is an internally inconsistent assumption. So, the physical assumptions that we make should also conform to the fundamental differential balances, that is namely continuity equation and momentum equation. For example, the momentum equation for this problem in the y direction told us that the pressure gradient is a function only of x. Okay. It is a very useful piece of information, and we use that in the x momentum equation to find out that dp dx and d squared u dy squared each must be a constant. So, the equations sort of tell us additional informations, and they also confirm to our initial assumptions. Okay. If the equations do not corroborate your initial assumptions, then that means that those assumptions are physically invalid. Okay. So, we make assumptions based on some intuitive ideas, okay, but those assumptions should also agree with the fundamental equations of fluid mechanics, that is the differential mass balance and differential momentum balance. Okay. So, at least in this example, we had no contradicting assumptions, okay. We had no contradicting results, okay, in our answers when compared to the assumptions. Okay. Now, another important point that we have to make at this juncture is that the fact that we have obtained one physically consistent solution does not necessarily mean that this will be the solution that is obtained or seen in experiments. Okay. The reason for this is that the Navier-Stokes equations are a nonlinear set of equations, and whenever you have nonlinear set of equations, you cannot prove that a given solution is unique. If you have a linear system of equations, differential equations, then uniqueness is proved always. A given solution, any given solution that satisfies the differential equation and boundary condition is the unique solution, there is no other solution. But such uniqueness proofs do not exist for nonlinear differential equations. Therefore, we are left to wonder whether the solution that we derived is the only solution, because in principle there could be other solutions. So, how can we settle the issue? The issue can be settled only by carrying out experiments in the lab. Okay. By carrying out experiments in the lab, you have to measure the flow rate for a given applied pressure drop and see whether the theoretical relation that we derived is valid, because you can compare the theoretical prediction with the experimental observation to see whether the flow rate varies with pressure drop in the same way as we have predicted. Now, it turns out that in reality that the flow rate relation, the flow rate versus pressure drop relation for a channel, rectangular channel, that is this relation, is valid in a certain regime for lower velocities, while when the velocities are very high, then this relation breaks down. Now, we are going to return to this topic a little later also, but I will just point out by saying that there is a non-dimensional ratio called the Reynolds number, which we will come to shortly after we are finished with differential balances. The Reynolds number is a non-dimensional group, that means it is a quantity that has no physical dimensions, it is just a number. Okay. It is defined as rho times the average velocity times the width of the channel divided by the viscosity. Okay. We will see later how this number naturally emerges and so on, but right now I am just telling you a fact that for a given fluid, what is fixed? Rho is fixed, mu is fixed. For a given channel width, 2b is fixed. So, Reynolds number is essentially for a given channel and given fluid, it is a non-dimensional velocity in some sense. So, as you increase the velocity, you are increasing the Reynolds number. Okay. When the Reynolds number is greater than about 1000 for this problem, for flow in a channel, then this assumptions break down, the flow becomes unsteady and 3-dimensional. That is not it, we first claim that only one component of the velocity is non-zero, that is the x component of the velocity. When the flow becomes, when the Reynolds number, which is a non-dimensional velocity at this point of view, at this point of time, we can just think of it as a non-dimensional velocity. When the Reynolds number is greater than 2000, or sorry 1000 for this problem, the flow in the laboratory becomes unsteady and 3-dimensional and evolves to a complicated state called turbulent flow. Okay. At which point our all the assumptions break down. So, this pressure drop versus flow rate relation will also break down. Okay. So, the relation that we have derived by making simplifying assumptions to Navier-Stokes equations, namely that the flow is steady and then there is only one component of velocity and fully developed and so on, they are not valid when the Reynolds number is greater than 1000 or so. Okay. But until that, these are valid and they provide an accurate description of what is happening inside the two plates of a rectangular channel. But when Reynolds number is greater than 1000, none of these predictions are valid. Okay. And we have to have a more sophisticated theories to understand and describe how fluid flows inside a channel in the turbulent regime, that is when the Reynolds number is greater than 1000. Okay. So, that is something that we must always keep in mind when we derive simplified flow solutions from the Navier-Stokes equations, because these are not always, there is no guarantee that if you obtain a solution to the Navier-Stokes equation by making physically motivated simplifications, it is not a priori evident that the solution that you get will be actually observed in the experiment, because the reason is there is no uniqueness proof. The solution that you obtain is not necessarily unique, because the Navier-Stokes equations are a set of nonlinear partial differential equations, and there is no reason for us to expect that a given solution that we obtain is the unique solution. So, having done that example on flow through a rectangular channel and having pointed out the key features of a solution, we now next move to another important example, flow through a pipe. Okay. So, imagine having a long pipe, okay, a rigid pipe, a circular pipe of radius r, radius of the pipe is r, and this ends of the two pipes are, let us say you have one end of a pipe connected to a huge reservoir and the other end of the pipe could be open to atmosphere. So, because of the virtue of this pressure head present in this, okay, let us say liquid is present, fluid is present here, and because by the virtue of this gravitational pressure head rho g h, okay, the fluid is going to flow in this direction. And the question again that we want to ask is, what is the relation between pressure drop and flow rate? And the reason why I am going to do this, there are two reasons why I am going to do this. One is that this is one of the most practically encountered flow geometry in chemical processing industries, that you have pipe flow in pipes of various dimensions, diameters in any chemical plant. Okay. The second is that from a fundamental perspective, this will also tell us how things are different when we go to a different coordinate system. For example, in the previous two cases, we have worked out two examples of the solutions of Navier-Stokes equations. One is plane coed flow, other is plane Poisson flow. Okay. But both these cases were amenable to solution in Cartesian coordinate systems, because the geometry is such that you can nicely use a Cartesian coordinate system to define the flow, to describe the flow, but not so in the present case. So, before I proceed with the problem, about the names, this is variously called as Hagen-Poisson flow, or pipe Poisson flow. Or simply pipe flow. Okay. So, the first thing to note is that, so since this problem is very similar to what we just discussed, namely flow in a channel, let us focus more on the differences between this problem and the previous problem. The first thing is, what is the coordinate system that we have to use? Here there is a natural symmetry associated with the circular nature of the pipe. Okay. So, you have a pipe like this. Okay. So, it is better not to use the Cartesian coordinate system, okay, and it is better to use a cylindrical coordinate system. So, let me quickly explain what is the cylindrical coordinate system. Okay. You have the three Cartesian coordinate vectors x, y and z. Okay. Any point in space is, okay, from the origin you connect it. Okay. How is it described in Cartesian coordinates? We decompose it into, okay, so let us try it in Cartesian coordinates. Any position vector is x times I plus y times j plus z times k. Okay. In cylindrical polar coordinates, we do not use x, y, z. Okay. Instead, we take the projection of this vector on the x y plane, okay, and the angle this projection makes with the x axis is theta, and the length from the origin of this projection, okay, length of the projection from the origin is r. Okay. R is the radial distance from the origin to the projection, and it is essentially the length of the projection on the x y plane. Theta is the angle the projection makes with the x axis, and z is normally z. Okay. So, the other coordinate is z. So, the three coordinates are r, theta and z, where r is the length of the projection the position vector makes with the x y plane, and theta is the angle between the projection as well as the x axis, and z is the normal z coordinate that you have in Cartesian coordinate system. Okay. So, any position vector is now represented as r e r plus z times k. Now, since we are now moving away from the I j k notation, we write this as z times E z. Okay. So, that is the way in which any position vector is described. Okay. Now, what is convenient about the cylindrical polar coordinates is that if you have a pipe, okay, so let us first draw the coordinate system. This is x, y and z. If you have a pipe, you can nicely place the center of the pipe, you can align the center of the pipe with the z axis, okay, with the z axis. Okay. So, you can nicely align the center of the axis of the pipe with the z axis. Okay. So, you are exploiting the symmetry of the pipe by just nicely placing the axis of the pipe along with the z axis of the cylindrical coordinate system. Okay. Now, so you have in any cross sectional plane, okay, you have r. So, you have distance from the center as r, okay, and theta is the, okay, theta is the angle made by the projection of any point on the x y plane, okay, with the x axis. So, that is r is this distance from the center, and that is theta. Okay. So, when fluid is flowing, we can align the flow to be in the plus z direction. So, there is a pressure gradient in the plus z direction. Okay. Now, what are the components of the velocity? The velocity vector is written as v r e r plus v theta e theta plus v z e z. Now, we are going to make some assumptions again like before. Again, as I mentioned just few minutes back, the validity of the assumptions can be tested only by checking the predictions of our analysis with experiments. There is no other way we can justify these assumptions right away. Okay. So, what are the assumptions that we are going to make? We are going to make the assumption that since the pressure drop is across the z direction, the flow must be symmetric around the theta direction. Such flows are called axisymmetric flows. By axisymmetric we mean no variation in theta direction. Okay. So, we make the assumption that the flow is axisymmetric. The other two assumptions we are going to make are as before: steady flow, velocity is independent of time, and fully developed flow, the flow velocity in the z direction is independent of the z direction itself. Okay. So, now axisymmetry also means that there is no theta velocity, because if there is a theta velocity, that is going to break the symmetry in the theta direction. Okay. So, not all points in the theta direction are equivalent if there is a theta velocity. So, theta velocity is 0, that is what axisymmetry means, and we are also going to use the fully developed and steady flow assumptions. Now, the next task in our hand is to look at the continuity equation or the differential mass conservation equation. Again, as I repeated several times, we cannot write the continuity equation in a steady in the vector form. Del dot, the continuity equation or the mass conservation equation becomes del dot V 0, but you have to look up tables in textbooks in order to write that in cylindrical coordinate systems for reasons that I have mentioned several times before in this course. Okay. So, the continuity equation in cylindrical coordinate system is as follows. Okay. Now, let us use the assumptions. There is no theta velocity, the flow is fully developed. So, V z is independent of z. So, all we get is 1 over r from the mass conservation equation, r V r is 0. Now, this implies that d d r of r V r is 0 or r V r is a constant. What should that constant be? Now, if you look at the pipe, okay, this is the r coordinate. At r equals the radius of the pipe, when you reach the radius of the pipe, there is no normal velocity, V r is 0. So, r times V r is 0 at r equals r. Okay. So, that constant must be, since it is a constant, it must be 0. Okay. If that constant is 0, then V r is 0 everywhere in the flow. There is no normal velocity. The assumptions of axisymmetry and fully developed flow conditions automatically ensure that there is no normal velocity, that is the r component of the velocity is 0. So, that is the information that one can glean from the continuity equation for this problem. Okay. So, what we have ended up is with the fact that you have a velocity field, steady velocity field V z, it is a function only of r direction. It is not a function of theta direction by axisymmetry. It is not a function of z direction because of fully developed flow conditions. Okay. Now, and only in that case you get the velocity in the z direction to be a function only of r. Okay. Now, let us look at the Navier-Stokes equation in all the three directions. Okay. So, let us, this is our pipe, this is the z direction, this is the x y plane. Okay. Now, let us assume that the flow is perpendicular to the direction of gravity. The direction of gravity, let us say, is in the minus, the acceleration due to gravity vector is in the minus y direction, and the flow is directly perpendicular to the gravity vector, that is the pipe is horizontal in some sense. Okay. So, if we do that, then the gravity vector, the acceleration due to gravity vector, because the gravity vector is pointing in the minus j direction, that is in the Cartesian coordinate direction. We have to write this in terms of the unit vectors in the cylindrical coordinates, which are E r and E theta. Okay. So, g is g times minus E y, okay, that is the unit vector in the y direction. Now, from geometry we can write E y is sin theta E r plus cos theta E theta. So, G is minus G sin theta E r minus G cos theta E theta. Okay. So, that is the acceleration due to gravity vector, and we have resolved it in the two directions, namely r and theta direction. There is no acceleration due to gravity vector in the z direction because it is perpendicular. So, all the, if you look at the r momentum equation, r component of the momentum equation and theta component of the momentum equation, all they will say is that the pressure variation is hydrostatic in the y direction. Okay. So, that is all they are going to say. So, there is no need to worry about the other two directions. Okay. Now, we are going to write the z component of the momentum, differential momentum balance, the Navier-Stokes equations. Again, to remind, the Navier-Stokes equations have different forms in different coordinate systems, because the gradient operators as well as the divergence operators, they are different in different coordinate systems. So, we have to look up a table. So, I am merely writing it for the sake of our convenience here, but you can look it up in any tables in many textbooks. Is equal to rho g z minus partial p partial z. Now, since it is slightly bigger, let me write it here, plus mu 1 over r partial r of r partial v z by partial r plus 1 over r squared theta squared plus partial squared. Okay. Now, let us use the assumptions to throw away terms. Flow steady, and there is no V r velocity, there is no V theta velocity, the flow is fully developed, there is no gravity component in the z direction, flow is axisymmetric, there is no variation of V z in theta direction, flow is fully developed. Okay. All these terms are 0, leaving us with only, just as in the previous case, you have mu times is equal to dP dz. And what is dP dz? Well, just as before, just to save time, I am going to invoke the previous discussion on channel flow, which we just did. Okay. We can say that this is equal to minus P at 0 minus P at L divided by L is equal to minus delta P by L, just as in the previous case. Okay. Now, so this is equal to 1 over r partial r of r. Okay. Now, we can integrate this in the following manner: d dr of r dVz dr is minus delta P r by L, or if I integrate this once, r dVz dr becomes minus delta P by L r squared by 2 plus C1. If I divide it by r, I will get r by 2 plus C1 by r. If I integrate this once more, I will get minus delta P by L r squared by 4 plus C1 ln r, because if you integrate dr by r, you get ln r, natural log of r, plus C2. Now, you have to evaluate this, you have to evaluate the two constants with the boundary conditions. Okay. What are the boundary conditions? The boundary conditions are V z at r equals r is equal to 0. This is no slip condition at the boundary, and V z must be finite at r equals 0. You cannot have V z to be tending to very large values at r equals 0. We will stop here at this point and we will continue in the next lecture.